our focus is going to be AI and our IoT in this session. And our next speaker will be Professor Irad Ben Gal. Irad is the head of the Lab of AI Business and Data Analytics, LAMBDA, at the engineering faculty in Tel Aviv University. Irad is a world-renowned expert in practical machine learning, statistical process control, and predictive analytics, with more than 20 years of experience in this field. And I can trust that even when he was a visiting professor in Stanford University, we have sent delegates from our center in Tel Aviv University to make sure that he is having a great progress there. So with this, Irad, this is our pleasure. Professor Ben Gal, please.
Thank you very much, Yaniv. Thank you for the organizers. Quite different than the regular years when we are having our meetings physically, but this is what we have this year. And I know it's late, so I'll try to be focused. We will be talking about federated learning. This is a new scheme actually proposed only in 2016 by Google, with a main intention to reduce communication and save privacy. However, in the field of AI, we see some more opportunities and challenges that are related to this type of learning. So I'll talk about it. This is the topic of a PhD student, Maharan Jazi, that actually also prepared this presentation. Maharan is from Ramallah. I think that is maybe, if not the only one, but one of very few Palestinian students that are studying at Tel Aviv University at the Faculty of Engineering, and we are very proud of that. Part of the work is a joint collaboration with this team from Stanford, Eli, Ariana, led by Professor Nick Bambos. So I'll talk about federated learning, just give some introduction and motivation. I assume that many of you know it already. I'll talk about the focus in our study towards learning, which deviates a bit from the classical communication focus when federated learning was introduced. And we'll show some kind of implementation in different data sets, just to give you some kind of, some sense of the challenges and the many factors that can affect the performance of this federated learning scheme. So federated learning in a way is part of what we call edge computing. And I assume that everybody knows that the idea is to move intelligence from the cloud to the edge and be as close as possible to the final component, device, application, or person, you know, everything that you see in this triangle in the basis of it. The advances, of course, if you do this learning at the level of those components, is to reduce latency. You don't need to transfer a lot of data, and you can actually reduce cost. You can use it, those applications in remote locations, even if you have some communication or, you know, internet problems. And of course, it also improves security and privacy, because in many cases, the data stays at the edge and there is less interaction with this public cloud servers, either at the node or at the data centers. However, it comes with a price, and the price, of course, is that learning has to be implemented and executed at the edge efficiently, okay? And this is a growing field. Already the market is, I think, more than $7 billion. And the applications are countless. So for example, think about another work that we did with Stanford is a personal health sensing. So, and many of us will carry on their bodies, either wearable or in their bodies, some sensors. And in one hand, you don't want to send this private information to the cloud. On the other end, you want to learn from a group of people about, for example, the propagation of a disease. So the ability to learn it on the edge and to send something to the cloud is very relevant here. Same goes to autonomous vehicles, where you want some computation at the edge, at the vehicle itself, but you need to learn many things about roads, about possible problems that could affect traffic in general, Internet of Things, SaaS, voice assistance, anything. I mean, there are really countless applications. Now, as I said, it comes with a price that you need to have an efficient on-device learning, because data increasingly is generated on those devices. It can be images. Think about your personal image data sets that can be classified, and then you need to be able to classify the level of that phone, or you do an NLP and text analysis of your emails, or you do this health sensing that I was referring to, and then you can actually try to take those models and upload something back to the cloud. And this is exactly the idea that came when people were talking about federated learning. And this is a simple scheme, again, introduced by Google in 2016. The idea is that you have a central server here, and you have a sort of a deep network. Actually, it can be any machine learning model, but let's think about, a large deep network that has, many, many parameters that are representing all those weights on the links between the edges. And this type of model is shared by the different devices, either phones or other devices. And what happens is that those devices learn based on their own data, and they send back only the weights of this deep network. And what you see here in the server is a sort of, averaging all those weights. There are several ways to accumulate all the information from those devices. You need to do some kind of taking into account, the size of the data and so on. But basically, you can actually, in each such cycle, update the model. And as you can see, the data, as I said, never leaves those devices. Only those weights are going back and forth from the main server to those devices. And we call it, when for such a cycle is called communication cycle. And when we talk about the number of clients, we talk about those clients below. When we talk about the number of servers or a single server, this is this guy on the top that gets all the information. There is a lot of information or a lot of questions related to configuration of this network that are associated with the way that data is shared. And again, the classic approach to federated learning is that data never leaves those edge devices. But when you try to optimize also the learning, you can think about some sharing of those data from the local servers to those edges. And then you need to, once you share some of it, or they can share it between themselves, you can think about a way that the best way that they will be modeled by their local machine learning models. And you can also consider the epochs, which is the time that you need to train those local models at each of those edges. So there are many, many parameters that can affect these learning schemes: number of servers, number of edges, number of communication cycles, number of epochs in each edge, the data distribution, and so on. And since it was introduced quite recently, there is no real understanding how all those parameters work. And this is what we tried to do in this research, sorry. So what we tried to do is to see if we can take this federated learning approach, and instead of focusing mainly on communications, you know, reducing the amount of communication and reducing any sharing of data, can we do something also to improve the learning, even at the price that we share some information, maybe partially between the server and those edges, or between the edges. So think, for example, if people are co-workers at the same organization, at least some of the data can be shared between them. Or if we are talking about a family, definitely some of those pictures can be shared between family members. And these, you know, partially shared, partially overlapping data sets can actually improve dramatically the learning. And this is what we wanted to check and see how all those parameters can affect the performance of the network. And again, parameters can be the data distribution, the number of communications, the number of epochs, anything that I just, those parameters I just spoke before at the previous slide. So what we did, as a first step, we simply did some sensitivity analysis that takes into consideration all those factors. We took several different models, starting from a very simple logistic regression, going to a more complicated deep neural network, but that is still quite simple, and moving on to a more complicated convolutional neural network. And we implemented it over different data sharing schemes. And we compared it also to the centralized mode, where all the data is actually kept at the server. And we implemented it over 3 different data sets: MINIST CIFAR-10 and XSS. So I'll say a few words about each data set, and we'll move to the conclusion. So the MINIST is basically the Modified National Institute Standard and Technology dataset that Jan LeCun was traditionally using for training and testing deep neural networks. It contains, 60,000 pictures of handwritten digits and 10,000 pictures for testing. And each picture is basically a 28 by 28 pixel grayscale. So it's in one hand, it's complicated enough, but it's not overloaded in terms of communication and the content of data. Then we have a more sophisticated or more heavy loaded data set, which is the CIFAR, which is 5,000 pictures that are actually color picture with 32 by 32 bits. So they are much more complicated than MNIST. And finally, we looked specifically, we knew that we'll give this talk in this conference on a cross-site scripting data set, where basically we are talking about injection attack targeting website and web application, legitimate websites that actually, I won't go over all this scheme, but basically what it does, this type of attack, it sends some malicious script to legitimate domain, and when the user is sending some HTTP request, this domain that was infected will basically send back an HTTP with a malicious script that will move those stolen cookies to the attacking domain. And the question here was whether we can actually find malicious versus benign scripts. So I won't go into the details of what we learned, but I will give you some kind of insights because we are short in time. So first, the XSS, what we see is that, of course, when we move to a more complicated network, this is the black line instead of the orange one. What you see is that the quite fast the network, the federated learning converges, and after 10 communication rounds, you get a very good classification between malicious and benign scripts. And the nice thing is that since the data is distributed between all those edges, what we see is that the federated learning actually performs better than the centralized approach. And I don't have enough time to go over it, but it's something related to what we call weak classifiers, the ability to take the same data sets that is shared between those edges, let's say, of the same organization, and at the same time learn parallelly, actually improve their results. And this is why the dashed line that are the central approach are below those rigid lines. Same happens with other data sets. Again, I won't go into details, but we see that as the data gets more complicated, this is, for example, the CIFAR dataset, the more complicated models can actually take advantage of the federated learning. And if we are able, again, to distribute the data well, the accuracy will be much higher. So I need to stop here. I will just say that the picture changes when data is totally not overlapping, which again is a classical approach of federated learning. And I will finish by saying that federated learning enables, of course, a distributed client device to collaboratively learn and share prediction model while keeping all the training data or most of the training data on the device. On-device learning, scale-up, machine learning, and AI, specifically when we're able to create those more agile and flexible data sharing schemes. And as the data and problems get more complicated, of course, the sophisticated model perform better under federated scheme. And there are many, many unsolved challenges. We are still in the beginning of this research that need to be addressed, including all those parameters that I was talking about before. So thank you. And Yaniv, the stage is yours.
Great. Thank you, Professor Ben Gal. It was really interesting, and we learned a lot about federated learning generally and about your research and efforts. We got a question here from the audience that I would like to ask you about, and I think that you touch it a bit on your conclusion slide, but can you maybe say a few words about the question if the federated learning, we hear so much in our conference about AI, so if the federated learning can improve AI in general and even with some applications, specific applications?
So indeed, I touched it, and the answer is yes. If you're willing to share some data, actually federated learning becomes something like ensemble. So different computers or edges can learn different parts of the data, but with some kind of overlap. And in general, when you talk about learning, it reduces the chance of local optima. So basically, since there are many, many learners that look at similar data sets, but not totally identical, the scheme is much more robust. You can learn from all of them, and you are more secure not to fall within, local optima when you apply those learning. So this is the general response. And of course, when you talk about specific application, this is very relevant to all those applications I mentioned. Just to mention, we took diabetes in LAMBDA in our lab. We took data from diabetes patients, and we shared some of it with the cloud, and some of it remained private. And by doing so, we were able to actually analyze and learn better the daily propagation or the daily patterns of insulin and sugar concentration in their blood. And this is something that we will see more and more. I mean, doctors will, instead of seeing you for 5 minutes and learning at that time what happens, they can both use those remote sensing to learn about you, and also get feedback from many, many other different patients in a similar condition, or that can be relevant to your condition. So this is the way that it can be used.
Great, thank you very much, Irad, for the answer and for the entire talk, and good luck with your research, and also like a national initiative that you are involved in. So thank you very much.